Right, so this is going to be a talk mostly about learning visual representation using them for solving image understanding tasks. Before I even start, I would like to have a sense for the audience. So how many of you are familiar with machine learning in general? Yeah, vast majority, that's great. And deep learning? Yeah, a fair bit. Okay, that's good. All right, so this is the starting point. It's actually a very simple one. So here we have an image like that. We call that X. And really what we want to do in the simplest case is to understand what the image contains. For example, we could pose the question whether that is a bicycle. So how can we do that? Well, if we use machine learning, what we would do is that we would collect a bunch of training samples, some which are positive and some which are negative, so images that do not contain bicycles. And the next step would be to look at this data in a sort of more abstract way as a point into some high-dimensional vector space where you also have your positive and negative samples. And then, well, you would learn probably a classifier, linear classifier, or linear predictor. So this is a function which takes X, which is now a vector, multiplies that by some vector of parameters W, gives you a number. If this number is positive, then you say, yeah, this is a bicycle. If it is negative, you say it's not. And then the gradient here, the color, denotes how strongly you are in your assessment, which is just reflected by the size of this number. Okay? Now, this is a story that everyone knows. There is another part to it, of course, which is very important, in fact, probably much more important, which is to say, what do we do when X is in fact not a vector? So what do we do about that? Well, the way we approach this is usually by computing a representation of the data. So what we do is take X, then we have a representation function phi, and we use it to map X to some high-dimensional vector, which lives in some d-dimensional Euclidean space. All right? So now we have this representation which takes X, our image, and gets a vector for us. And if we do that, even if X is not per se a vector, we can use this transformation to compute our linear classifier. So we can still use the same simple linear rule to associate a number to X to decide whether it's a bicycle or not. And if you're smart enough, or lucky enough to find one already in the literature, well, you can, by choosing phi, work with any sort of data. It can be images, can be text, can be sound, can be videos, and so on and so forth. So the key topic of this talk is really how to design these representations. So in computer vision, we have been working for at least 15 years, I guess, since the, well, maybe 12 years at least, since the beginning of the millennium, I would say, on hand-crafted features. So this is when machine learning started to become popular as a computer vision tool for image understanding. And so people were working, say, with supervector machines for the predictor, so linear classifiers. But the problem is, how do we come up with the features to feed these machines with? And people were just designing them by hand. So if you work in vision, you will be familiar with concepts like saved hog, all the plethora of features that people have been developing to do that. So you do something meaningful by using your ingenuity, by designing these features. You can also work with kernel embeddings. Kernels has been a sort of very big area in the machine learning as well as in vision in the past years. And so these usually work on top of some hand-gathered features, but they change in a way the meaning of the features by changing the notion of similarities, which is embedded into these representations. But these are not learned. These are also handcrafted. Now, you can do something a little bit more general, where you start to introduce some learning, not just in the predictor here, but also in the representation part, for example, by doing metric learning. So here, you change the metric, which is, say, represented by this kernel embedding, by learning, actually, Mahalanobis metric in that space, which is tailored to your data. I'm going to see much later in the talk what that actually means. And now you feed that to your SVM to perform a prediction. So here, the representation itself is somewhat learned. But what I would like to talk to you more about today is really this box here, which is deep learning, in which not only this bit is learned, but in fact everything, from the image pixels directly to representation, and in fact including also the predictor itself. Although this distinction between representation and predictor is still meaningful and very useful. Okay? So here's the content of the talk. It's in several parts. It's fairly specialized. I'll try to make it as interesting as possible to a general audience. We're going to start with some preliminaries for people which are maybe less familiar with deep learning, just to set also the notation. And then we'll go through some examples of applications of CNNs, and finally some work we are doing to try to understand what these things actually do. So here's a typical convolutional neural network or deep representation that we use in vision nowadays. So we have an image, X as input, and then this goes through a sequence of nonlinear blocks, which compute something out of the image, statistical features. And the first 5, in this case, this is a specific example of one architecture which is called AlexNet, which was the first very successful architecture of this kind in image understanding, I should say. Well, so the first couple of layers here are called convolutionals. Then you have some fully connected layers. I'm going to show you in a minute what these are. But basically, all these operators extract some information from the image by using a combination of linear and nonlinear operators. And you chain them up together, and eventually you get a code, which is your encoding of the image computed by CNN, or the representation of the image. And you can use this for classification. Or maybe this is directly a class label. So decoding this into an answer to your problem is trivial. This could just be a bit which says this is a bicycle. Now, there are 2 views of this. One is that what we're doing here is computing an input-output relation, so something that goes to the image to an answer to your problem, say image classification. But the other one, which is actually more interesting, more useful, is to look at this as a way of computing a chain or representation for your data. Okay? So what are these building blocks that compose a CNN? Well, the most simple one, but probably the main one, in fact, is just a bank of linear filters. So here, this little box, 3-dimensional volume, denotes an input image, or later in the chain, some intermediate feature. This has a width and a height, and has a depth. So in the case of RGB images, this would be 3, and this could be, say, 640 by 480. So this is just an image. Then they apply to that a number of linear filters, which basically means you convolve this by one of these little blocks here, which is a filter in itself. And that is also has also a bias associated to it. You slide this through the data. This becomes basically a local multiplication between 2 vectors. And you get an output element here. You add an offset. And this allows you to compute from this input image an output map, which has a value for each location, spatial location in the input image, and has a number of channels which is equal to the number of filters you're using. So each filter itself is multidimensional in the sense that the data has more than one channel. The output of that has also more than one dimension. The number of dimensions depends on the number of filters you're using. Okay? Now, there are other things which compose a CNN typically. So one is downsampling. So as you go along this architecture, typically you want to lower the resolution of your representation and increase its dimensionality, because the representation is in a way becoming more abstract. You have, of course, nonlinearities. So these operations are still linear. It wouldn't be very meaningful to chain linear operators together, because eventually the results would still be a linear function. So what we need to do is introduce nonlinearities. A type which works well in practice is this ReLU. So you just take a maximum between x, which is your data, and 0. There is spatial pooling, which essentially you perform some sort of filtering, but this is non-linear. And what it does is not convolving the image by a number of weights, but is instead simply computing the maximum response of one of these featured channels within a small region in the image. And you have many other blocks. For example, there are usually being used a normalization block in which you take at one specific location a bunch of features which are stacked into a column, and you normalize them, for example, by sliding a window over these featured channels and performing some normalization operators locally. So it doesn't really matter that you understand in detail what all these blocks do. Probably most of you understand them anyway, and people that are not familiar with them would not appreciate why these ones are being selected in particular. Suffice to say that these are good building blocks that allow you to express very complex functions while at the same time being able to train them. So this is what this looks like with our AlexNet architecture. So you have a sequence of convolutional features. Each one of these blocks is really a sequence of linear filters, downsampling, computing this ReLU, max pooling, and sliding L2 normalization across featured channels. Some of these blocks might not be performed everywhere, but at least filtering and the ReLU are performed at all layers. Now, these fully connected layers here are just layers of this type, except that now the dimensionality, the spatial resolution of the image has been reduced to 1 by 1. So at that point, Applying a filter to your data means that your filter is just as large as your input image. Okay? This is why we call them fully connected. It's not a local operator anymore. It's applied to your data at that level on its entirety, on the whole spatial domain. How do we learn this? Well, we set this up as an optimization problem. So we have an input image. We computed its encoding, which could just be a predictor for the class label for the object. And then the next thing we do is we compare that with the ground truth label for the image. That gives us a loss or error function. We have parameters which are just the parameters of these filters throughout the architecture. And this is what we want to learn. We want to learn those in such a way that we minimize this loss. That means that we're going to choose parameters for all these filters in such a way that the prediction that this architecture makes about this image is as close as possible to the ground truth, which in this case would be guessing the label of the image. This is a bicycle correctly. Okay? So we can formulate this as minimizing in these parameters this error or average loss. Of course, you don't do that from a single image. You do that by averaging many images. Why? Well, because here you have typically 100 million parameters. So these are very, very big models. And you need those parameters to perform well in computer vision tasks. But in order to learn millions of parameters, then of course you need a lot of images, as many as possible. So typically, what we do is we use roughly 1 or 2 millions for this type of architecture. So this was, in fact, one of the contributions that allowed machine learning to actually, machine learning community to actually build the first example of architecture that would work very well for, if you say serious, from a computer vision perspective, image classification problems, was the availability, finally, of a very large collection of annotated images. The best known example is ImageNet. And of this, we typically use a subset of 1,000 classes, although there are many more in ImageNet as such. And for those, we use 1,000 examples per class. So we have 1 million images to train a network, roughly. Now, how do we do that? Well, we use stochastic linear descent as a online learning optimizer, which means that you visit a point at random in your data set, training set, compute an approximate gradient based only on that single point. You do a gradient step, you repeat. So this in practice means that you have to visit your data, these million images, maybe 60 times overall before you are able to converge to a decent model. And if you're not careful how you do this, then you might end up training this for years because this network is actually pretty big and evaluating it can be expensive. So the other ingredient which is very important to make this practical is the use of a good computational architecture. So typically this is only feasible if you use, for example, GPU hardware, FPGAs or something like that. Okay? Or you have a very, very big computer cluster. No, but these days this hardware is actually pretty cheap, so you can train it in your bedroom, and this is what how the AlexNet was obtained the first time. So it's not that scary. But it was scary 10 years ago, definitely. There's plenty of software you can use to do it. Some of these packages are really good. Some of these I'm sure everyone knows about them. Like Theano and Torch. Berkeley Café is very well known in computer vision in particular, whereas the other two are much more general. We also have our own toolbox, why not? So this is called MatConvNet. The difference between this and the other ones is that this is directly interfaced to MATLAB. So if you're a MATLAB guy and you like to use MATLAB for prototyping, this is probably the easiest one to use. It's very good for very fast prototyping. And the thing we did here was to break down these convolutional networks into very simple building blocks like convolutional layer, ReLU, and so on, make them available in MATLAB as GPU-optimized functions in such a way that now it's possible to recombine them very easily to create an experiment within architectures. This is all I want to say about that. So if you're a MATLAB guy, you might find this useful. All right, so this is enough preliminaries, and now I want to start discussing essentially the new stuff. So first topic is transfer learning with deep filter banks. And in fact, the first subtopic of that is just transfer learning. Now, this is one of the most interesting features, I believe, of deep learning. So deep learning is not just good because it gives you very good performance on the data you train for, and that could be, for example, the ImageNet dataset. It is very good because it actually learns a representation which turns out to be useful for many more tasks. So what we're going to do is now look at this case in which we have an image, and we divide, so we are our subdivision of the classification process in 2 steps, computing representation and then computing on top of that a predictor. We're going to fix the predictor to be something very simple, a linear supervector machine. And now we are going to ask ourselves, what's the best way of obtaining this representation? Now, last year, what we did was to do a fairly careful analysis of methods that were available back then. In particular, we wanted to answer what happens if you try to push as much as possible classic shallow representations, so basically hand-designed features like the improved Fisher vectors, which was essentially state-of-the-art in image classification before deep learning, or you replace this box with features which have been trained, for example, ImageNet, but we want to use them for a whole host of tasks. And the reason is that, well, these deep networks require lots of training data to be trained, so if your data set is small, you cannot really use them as long as you didn't initialize them from some other data set. So the ability of transferring information is extremely important in practice. So we did compare 3 architecture, which was representative of architecture types which were popular at the time. Nowadays, the state-of-the-art here would be achieved by different networks. The main difference between those is their size, so small variation, but they can have a quite significant impact on the performance of the networks themselves. So this is how this transfer learning looks like. So we are training a network, say on ImageNet. This has all the building blocks we have just discussed. Now we're going to take the first n layers of the network as a generic representation. So that means that we're going to throw this away and get output, for example, of fully connected layer number 7, and use that as a representation to feed it to a predictor to perform classification on a data set which is not ImageNet, like this. So we take the output of that, we feed that to an SVM, and we perform classification on a different image database, which could be Pascal, for example, if you're familiar with it. It's just something else other than ImageNet. Okay? Now, if this feature are general purpose, then this should actually work, and it should be possible to learn a good predictor, although now you learn only this box when you switch your domain like that. And in fact, this is exactly what happens. So this is a slide from this paper, The Return of the Devil is in the Detail, where we did this analysis of these networks. You can see here the best performance you could get just a few years ago on this data set with bag of visual words, which you're familiar, is probably familiar to many of you. In the same family of models, we have the Fisher vectors. This is sort of an advanced version of visual words, if you like. This is what was possible to do, what the results was achieved in 2006. In 2011, after several years of work, we were able to improve this by a fair bit by tweaking the Fisher vectors and pushing it as much as possible. But then you replace these Fisher features with convolutional features, and there's a huge, huge jump from 68% integration accuracy or mean average precision, if you know what that is, to 80%. So this number here, if you're not familiar with the mean average precision, means that roughly 70% of the images in this case are classified correctly, okay? Very roughly. I know there's some horrified faces by this explanation, but this is decently good approximation to what this actually means. So it means that in 2011 we were able to recognize correctly 70%, and in just 1 year, just by switching feature, this went up to 85%, and now this is actually hovering over 90% in 2 years' time. Okay, and this was maybe 2004-ish. So you can see how fast the improvement in performance has actually been. But it's not just image classification we want to perform. So there are many other problems we want to solve in vision. So here's another one which I like a lot. So this is a problem of text recognition. So here we have a bunch of patterns. And what people have done typically in vision about texts was to recognize their materials. Now, this is a very interesting problem, but what we wanted to do here is to move beyond that and get computers that are able to solve human-centric applications. That includes the ability of a human of describing these patterns by associating to them intuitive words. So for example, this could be zigzagged, this could be veined, this could be swirly, and so on and so forth. So in order to study these perceptual properties of images, we have developed a data set that is representative of them. And this is something that might be of interest to you. Well, here's a reference, and the data set is available online for experimentation. Now, this is just one example of what you might want to do with texters. More in general, you often find the problem of taking an image and selecting a small subset of it and want to answer a question about that. So it could be this textured attribute recognition, so saying this is banded, blotchy, checkered, and the grid. But it could also be material recognition, so you want to know that this is brick, this is ceramic, this is carpet, this is fabric. And crucially, all these are not entire images, but just small image subsets. And the same you want to do when you want to detect objects. So if you want to say that here there is a sailing boat, it's not enough to say that it's somewhere there in the image, but you were actually to pinpoint its precise location in the image. So you need to tell something about a subset of the image, not about the image as a whole. So how do you do that? Well, this is the classic way people have done it. So you would start from an image, then you would start proposing a bunch of possible boxes that would contain your object. Okay. This you can do either just sliding all possible windows or just finding some machine learning trick to actually get a short list of possible candidates which are likely to contain meaningful objects in the image. And there is a whole industry of computer vision papers about this problem. Now you have found it, you have one of these boxes, you crop the image and you resize it to a size that is suitable for your representation to work with. In the case of a convolutional neural network, that means that typically that this image has to be a square of a given size, a given resolution, and then you can classify the object. So what do you think is the answer here? What I'm trying to look for here? Is this a ball? What do you think? Is that a good answer? Well, you don't know. So what I was looking for here was materials, and one actually wanted to recognize the cloth. All right. So this resolution, working with this resolution is actually not enough very often. So working with boxes, it's okay. You can go a long way by using it, but sometimes you really want to pinpoint smaller detail and segment out an object from the image and say, this is what I mean, and this is a piece of cloth. Okay. There are other issues with this approach. One is that it's very expensive because you end up recomputing your representation for all the sub-windows you have obtained. So every time you crop an image, you have to recompute your CNN from scratch. And OK, with a GPU it's fast, but if you have thousands of windows in an image, it's still a bad idea. And then you get distortion because, as we said, typically these networks, by their design, at least the old versions, would accept just as an image would have a fixed aspect ratio. So if you're detecting a pedestrian, well, to feed that to the network, you need to squash the pedestrian into a square. So it becomes like a Pac-Man or something, right? So probably not a very nice thing to do to this human. So what can we do instead? Well, here's one thing we can do. So we can go back to our roots and look at what people were doing before CNNs. And so in that case, the computer vision pipeline, the computation of the representation was actually broken down into two bits. The evaluation of a set of nonlinear filters, like dense shift, and then pooling those filters into a vector that would become your representation afterward. Okay, so two steps. An evaluation of a bank of nonlinear filters, local features, and then pooling. Now, after this, you get representation, and you can compute your predictor. Now, we can do the same with CNNs, actually. So what we can do is, if instead of waiting up to the point where we use the fully connected lasers here, we branch off earlier, where we have convolutional features, well, then it turns out that because these features operate as a sequence of local operators, a stack of numbers here, so you take a location in your feature map, and you look at all the features that are mapped there, would actually correspond to a description which is localized in the image. So it would actually effectively work as the output of a nonlinear filter. So you can take those instead of traditional features like dense shift, and use them combined with some pooling encoder to come up with a representation of the whole image and then perform your classification. Now, sorry, this box should have been called encoder or pooler, in fact, not predictor. And then you feed that, so this takes your local features, maps them through an encoder or a pooler into a single vector, and then the vector is used to perform prediction. Okay? Now, so this is what we can do then. So we can take an input image. We can compute either convolutional features that belong to a CNN, for example, train on ImageNet, or we can go with a traditional feature like dense shift, and that we can pool in different ways. We can either use the fully connected layers of a CNN, or we can use, for example, something like the improved Fisher vector here. This results in a vector, which is a descriptor for the entire image, or for a region in the image, because then this pooling operation can actually be applied to any subset of the image too, and that you can map to a label. Okay? So what's the advantage here? Well, there are several. First of all, this performs better, and I'm going to show that in a minute. Second advantage is that this is a lot faster when you want to perform localization or detection or segmentation. Why? Well, because now, instead of recomputing your representation for each subwindow, what you do is you compute the filter back once, everywhere, and then you pool, but this is a fast operation, the information from this filter bank in the window that you want to classify. So instead of recomputing the whole representation from scratch, you only integrate the representation, which is computed once for the entire image, in the region you want to describe. Okay? And doing that is a lot faster. So we apply this to many, many different problems: text analysis, genetic object classification, fine-grained object classification, semantic segmentation. And we got pretty much better results than using CNNs in any other way that we could possibly think of at the time. So this is a very good way of using CNNs if you want to apply them to, if you want to do transfer learning with them, using them as filter banks as opposed to using these fully connected layers. Now here's a table with many results. Of course, it's impossible to read it, but if you're interested, we have many such nice tables in the paper, so if you really want to know about the details. Now let me just zoom in into one of these rows and show you the sort of results you can get. So this is one particular data set, which is called MIT Indoor Places. So this is a data set in which your images contain example different scene types, and your goal is to say which scene it is. For example, it could be a bedroom, it could be a bar, it could be a lecture theater, and so on and so forth. So here's how the performance works. So this is the performance that SIFT with Fisher vector achieves on that data set, say about 50%-ish. Now here we are evaluating 3 different convolutional networks. AlexNet, which was the old architecture we were discussing before, VGGM, VGGVD. This is what was best, I guess, last year, at least from our group. And this is the best net we have at the moment, which was highly competitive. So this, I think, scored either first or second, depending on which task you consider in the ImageNet challenge last year, which is well, essentially the international benchmark for the image understanding at the moment, where everyone competes. So even Google and maybe even Yandex, I don't know. But anyway, so now you have 2 ways of performing classification there. One is to use this feature plus R. So R stands for region, and it's actually a bit of a misnomer. The reason why we use that is because we were comparing at the time with RCNNs, which would just use your fully connected layers to perform classification. What this means is basically now we take an image of this scene, and we extract the features out of the fully connected layers, and then we perform prediction by linear SVM. So that's the old way of using this feature for image classification. Then there is the new way, if you like, which is really a combination of 2 old ways, which is extracting these convolutional features out of, say, Conv5, which is this last convolutional layer in AlexNet, and then computing a Fisher vector on top to aggregate them into a single vector of numbers. Okay? And this is sort of improvement you can get, which is actually quite dramatic. All right? So from 58 to 76 in this case. And if you use VGGVD, well, first of all, what you notice is that as you switch from one deep architecture to another, there is a big jump in performance. But the biggest jump that you get is because now you're using this architecture a bit better by extracting information from the convolutional layers instead of the fully connected ones. Okay? So this is to show that both improving architecture helps, but also that how you use this feature computed from the architecture is actually very important. All right? And by the way, this is the previous state of the art. So you can see which probably is already using CNNs, I would guess. Yeah, this is another CNN method. The previous state of the art without CNNs would have been right about here. Okay, so big improvements. All right, so before I move to the next part, are there any questions here? Yeah.
How many scales do you use?
All right, good question. So when we perform this, when we compute this filter bank, if you were to use dense-sift, you would compute this at different resolution of the image. We do the same for CNNs. And we have experiments where we change the number of scales we use and can go from, say, 4 to 10. And there is a bit of improvement if you sample more densely, but not consistently, not for all data sets, mostly because some data sets, very fine information is actually confusing for the classification problem. So using more scales helps, but with 4 or 5 scales, it's already okay.
For detection task, you use all the scales or some most important scales?
Yeah, we use all the scales. We use all the scales. We're not thinking too hard how we do it. So we trust the CNN to be able to learn away difference in scales as well, to be honest. Okay. All right. Yeah.
Did you use an image context just, or did you try to use
on the box. Well, we use a little bit of context, and I'm not sure we did try that, but it could help, definitely. So the question is, can you use local information as well as global information for another image? The answer is yes. This is the standard techniques used often in vision. OK, so second part, another application, actually. So this is about text spotting. And the reason why I like it is because it really shows how amazing sometimes these networks are when you don't really want to think too much about what you're doing. So here's the problem is we have given a natural image. So natural image is defined as something that you would take with your camera in any sort of common situation. For example, why not taking a snap of this tea bag? Why would you do that? I don't know. So that's a logical thing to do, right? But at the end, now you want to read the text in this image, and well, it's like OCR, but it's generally a lot harder because it's a lot less constrained. Most of the image doesn't contain text. It's just a small portion of it where this text is found, has to be found. And the text usually is also pretty bad. So in this case, it's out of focus, but there are other nasty things that can happen to it. So how do we solve this problem? Well, so two-step approach. The first thing we're going to do is to have a way of proposing windows that might contain text in the image. And I'm going to explain later how this works. But mostly I want to focus on the second step, which is classification. So now we do have this window, which contains a word, and we want to tell which word it is. How do we do that? Well, the obvious thing is, well, this is a word is a set of characters. So what you can build is a small classifier, maybe a small CNN, which recognizes individual characters. That's OK. People have done that. But we want to be dumber than that. So what we want to do is we take this and want to directly map it with the CNN onto that. OK, directly. What does it mean? Well, it means that we do this. We do a massive classifier. So we take our input image. We squish the patch to a fixed size. This is horrible. As a computer vision peer person, this should make your skin crawl, right? So it doesn't matter how long this word is. It's always going to be 100 pixels long for our network. So if that contains the word the would be just like that large. Okay, so this would stretch your data. But we don't care, because we want to be dumb. Then we compute something which is very similar to AlexNet. These are the details of the size of the field is 5 by 5, 3 by 3, numbers of fields you have. These are fully connected layers. Okay, this is very similar to AlexNet. The only thing is that we downsample the image less because the patch is so small. And then eventually we apply a classifier on it. And this classifier has to decide whether this is any out of 90K possible words. Okay, so this is a very large classifier. But we don't care. We just train it blindly, and we hope for the best. Now, this guy has 500 million parameters, so we're going to need to do something about that. So how do we train it? Well, first of all, we're going to need lots of training data. So we want to train 90K classes, and we want to have at least 100 examples for each word. So we're going to need 9 million examples. Then for training, we use the same stuff as you use for CNNs in general, so SGD. Now, here's one issue, which is a bit of a technicality, but it's actually quite important if you want to do this in practice. So in SGD, you typically don't sample a point at a time alone. You sample a mini batch. You sample maybe 200 images, and you compute the average gradient for those. Now, it turned out that if you want to train a classifier, typically your batch size should be representative of 1/5 of the total number of classes you have. Now, if you do 1/5 of 90K, that's 18K. Okay? So a mini batch will have 18K images in it. So it's not a mini batch anymore. It's a gigantic batch. So that's a no-go. So we don't want to do that. So what we did was to do incremental training. So we trained first on a smaller subset of classes, 5K, which are sampled at random. Now, once those are trained, we add 5K more, and we train those, and so on and so forth, by freezing the weights of the predictors for the previous classes. Okay? Now, this is a very simple idea, but works very well, and is very useful in this context. How do we train this? Well, that's the other bit of magic, in a way, that there is here. So we want to use syntactic data. Okay? So you might think that the right way to do this, and this is what a computer vision person would think, is you go out there, you collect example images, you crop by hand words, you construct an example training data set, and you train from that. Sure, you can do it, but it's very expensive because you need 9 million examples. So instead, what we do is we synthesize them, and these are examples of the synthetic text we have. As you can see, it's pretty varied. So how do we build that? Well, first of all, we sample a font at random out of Google Fonts. They have about 1,400 of them available. Then we add border and shadow. We do some perspective distortion. We add noise, quantization noise, salt and pepper noise, and so on, JPEG compression distortion. And crucially, I think we also mix this font image with a natural image which is randomly sampled out of the data set to add a little bit of background to it. Okay? So it's a simple pipeline in which all these steps are randomized, and it goes from and can generate a sort of nice variety of different appearances of text. And so we have 90 million those. And actually, before I move to that, the key message here is, although this is a synthetic data, if you train your system out of that, you get state-of-the-art performance on real images. Okay, so this is a case in which synthetic data seems to transfer perfectly to the real case. Of course, it's text, so you would imagine that this is easier, for example, than generating monkeys, all right, with computer graphics. But nevertheless, it's not obvious that it should work. So if you spend a little bit of time creating this pipeline and make it nice, it does work actually very well. So this is a slide of the overall system. Don't want to discuss this too much. Suffice to say that take an input image, you generate these proposals by using some random forest-based proposal generation system, plus something else. You get down to a short list by doing some simple cheap filtering out of that. And eventually you get this bunch of candidate windows, which might or might not contain a word. Now you need to decide which ones are good and which ones are bad. To do that, you try to recognize the text in them. So we also have a class which say, okay, this actually is not a word. And so at this point, we do both filtering of bad bounding boxes as well as recognition of the text for the ones which are actually good. Okay? And there is some post-processing to merging potential duplicate detections, all annoying things that you have to do if you want to get good performance. The key really is this classifier that goes from these image patches to a proposed score for a word or background. So here's some examples. Works fine. Amazingly, works for some pretty hard fonts as well. And here again, actually. Doesn't really have many problems with patches which are around the corner or maybe partially truncated, still working fine. So these are example of text spotting. So here the goal is to put a bounding box around the text and say this is the word colonial, right? Now there is another thing you can do, which is text retrieval. So here we have a large data set of videos. In this case, this is a BBC. And what we do is we want to retrieve all images which contains the word Boris Johnson in it. And so we want to retrieve videos based on the text which is in the video itself. And here's some more examples. Now, but examples are boring, so what I'm going to do, if I can, is show you a demo of that. Might as well, right? Okay, so here's the demo, if I can find it. Yeah, that works. Okay, so this is just an animation, by the way. It's not doing anything particular. So this is indexing a couple of million images in this BBC News archive we have. We have an ongoing collaboration with the BBC to work on their data that has been going on for many years now. And we are indexing, I think, something like 10 or 30 million frames, BBC videos. Now, this text recognition engine has been run before, so this is now pre-indexed. But, so I search for Sony. Where is Sony? Sony is here, for example. Okay, right there, I guess. Okay, yeah, right. Let's see whether it has. There are some more interesting cases. I don't know. Yeah. Okay. So it's pretty bad as a font. It's not great at all, but the system is still robust enough to do it. What could I search for? Well, you know what? There are some suggestions right here on this front page. News is an easy one because, well, news is everywhere. This is also news archive, so you wouldn't be surprised by that. Of course, most of the results you're going to get are just boring captions. But, well, anyway, so down here. Oops, sorry. Down here, right? As you can see, works even if the text is somewhat cropped. Although I don't understand why, because this should be overlaid on top of the frame quite nicely. But yeah, maybe the BBC is not as good as it was once upon a time, so they're not able to center text anymore. I'm sure it's also going to make some mistakes, so maybe this looks like a mistake, for example. Unless, yeah. So, yeah, so this was a pretty extreme case of distortion. So of course he only has, so in this case we should have rejected it, but it's still text and he has to choose between a dictionary of 90K words. So anyway, so you get a sense how the system works. Okay? So this time later we're going to show you another demo on image recognition instead. All right, so this actually I need to show you. So far what I showed was basically a nice application of CNNs where you really want to be dumb and you want to get good performance out, and what you can do is just use lots of training data, a big architecture, and it's going to solve your problem. Any question? Yeah, I think there was one. Yeah, two actually, yes. Right? Yes, he's looking for a, so it's not looking just for a tight box around the text, he's looking for a bit of boundary. Yes, that's true. Yep.
So in the paper you tried something much less dumb, some smarter encoding of labels, and it didn't work. So could you comment on that?
Well, so there are many things you can do, and so for example, if you want to be generic in text recognition, what you want to do is get out of your dictionary. So 90K is a lot of words, and it works for mostly English words, but if you have first names, for example, or surnames in particular, then these usually are not in a dictionary. So if you want to recognize those, it's actually quite interesting. You need to go beyond that. So what can you do? Well, then you can revert back to an approach which reads individual characters, or you can do mixed approaches in which you read maybe triplets of characters, n-grams, and put these things together to try to come up with a classification of your word. Now, so this tends to work worse than just this system that recognizes the entire word. I guess the intuition is that on the one side you're solving a problem which is a bit harder, right? And because it's not constrained anymore with a dictionary. And the other side, well, so in this case, the CNN has an opportunity to look at the entire word and try to optimize the decision based on the entire evidence. Whereas if you break this down into individual recognition bits and try to glue them together by hand or by some other statistical model that you can come up with, well, maybe that's not as optimal as just training everything together. Okay. But you know, your mileage may vary. Maybe very well be possible that you could do that and get state-of-the-art performance still. Yeah, I don't think I actually said about the performance of the system, actually. Maybe I should have. There are a bunch of data sets where you can evaluate this. One about corrupt word recognition accuracy, and the other one is end-to-end text spotting accuracy. So this is just evaluating how well you recognize your words once you have the bounding box, and this is how well you do, how well your overall pipeline does. And it turns out that this system at the moment is actually state-of-the-art in all these standard benchmarks, and is even beating Google Photo OCR, which was sort of, if you want to call it, a little breakthrough last year using CNNs for text spotting. Though this is performing quite a bit better than what they had. And the same is true for text, so this for recognition, the same would be true, I guess, for text spotting. Okay? So again, many numbers, if you're interested, you can look them up in the paper. But it does work objectively quite well. All right, so now I'm going to move into the third and then fourth part of the presentation. So CNNs are nice, but so as I mentioned so far, what we did with them was to be quite dumb. Now we want to stop being dumb if we can, at least going forward in the future, and we try to get to do that. What we want really is to get an understanding of what these networks actually do. And to try to do that, one would think you can try to do is to visualize what they actually compute. Now, this is a bit tricky, but it's actually fun, so I decided to present it here today. All right, so this is what this looks like. So we have a CNN, an input image there, and then we compute a bunch of features, one for each of the layers in the CNN. So the CNN itself is a collection of possible representations of the image. And what we would like to do is to be able to say what information is being computed or preserved about the input image at each one of these layers. So how can we do that? Here's one way to try to get some insight into it. So you can take your representation, so you take X, you evaluate it up to some point here, for example, 5, and then you try to invert this process and go back to the image. Okay? So you try to compute the feature, the representation, and then the inverse. Now, in general, this mapping is not invertible. It might or might not be, but in general it's not. So you cannot really do that. So what you want to do instead is to find not a reconstruction, or sorry, the reconstruction, but a reconstruction. So you want to find any point in the pre-image of this map. Okay, so you want to find any point x star that would give you the same representation as x. Now, by looking at how x and x star are related, so which sort of images the network would confuse based on the representation that it is evaluating, is computing, then you can understand a bit of the sort of invariances the network is encoding. So the pre-image problem is that, well, we do not have a unique inverse, so how can we find x star? Well, one way to do that is to minimize the difference between your given feature and the feature you're trying to reconstruct by finding x bar. So you want to minimize this difference by finding the optimal x bar and call that x star. To make this unique and also to recover some of the information that the representation loses, which is sort of generic low-level image statistics, then we want also to regularize here by having this functional there. Now, this functional should be as generic as possible because we don't want to introduce too much a priori information on this process, but at the same time, ideally, we would like to make our inversion on the space of natural images. We don't really care what the network does for other images in principle. So this should capture this idea that x bar should also belong to this set of reasonable natural images. Now, we don't really have a very good way of doing that. We have some proxies, which are very weak, but nevertheless good enough to get some results. One of them is to just compute the gradient of the image at each point, then integrating its beta norm, and beta could be 2 or 1. So if it is 1, you get a TV norm regularizer, and if you get 2, you get basically diffusion, isotropic diffusion. Basically, this means that when you do this reconstruction of the image X from the feature, you impose some smoothness in the result, but very generic kind of smoothness. Now, you can use this for any representation. It's not just for CNN. So here's another one, which is HOG. So if you are working in computer vision, you definitely know this. If not, here's a 5-second explanation of what this does. So you take an input image, and you want to compute a representation of the image, which is useful for classification. One thing that works well in practice is you take local patches in the image like this. These are the pixels magnified. You compute the gradient at all these spatial locations, at all pixels, and then you compute a histogram of oriented gradients, which basically means you accumulate these arrows based on their direction on different bins on the histogram. And then on the histograms, you can see by unfolding this circle as a linear structure. So this becomes just a histogram that to which you apply some sophisticated normalization that has been shown to improve performance in practice. Okay? At the end of the day, what this means is that the image is being encoded like that by your representation. Now, a glyph here means that most of the gradients in this region follow this direction. And you can see here that this is essentially capturing, in a sort of vague way, the shape of your cat head. Now, we can play this game. So these are two HOG representation of two images, and the question is, what are they? By the way, I didn't invent this. This was by a group in MIT, Antonio Torralba. Okay, so what is this? Come on. A dog? What's this one? Or that one? What? Top one is what? A dog? No. Yeah? The bottom one is, okay. Bottom one, we have a dog. And the top one? The top one is a dog. Okay, so we have dog twice. No. So we have dude, okay. Just might actually look like a dog, but now you can see that there is this edge here, and that corresponds to that edge in the image. And yeah, people were able to spot legs here, but it was actually a horse, a posterior horse, in fact. Now, you might think that then if a computer works on this representation, it shouldn't have any hope of recognizing there is a human there, but of course there is a trick. And the trick is that our visual brain is not really designed to recognize this sort of patterns, it's designed to recognize that. Now what we can do is to play this inversion trick and try to recover X from HOG X. And so yeah, this group in MIT came up with a solution to that, and you can go from here to, from HOG X to the inverse of that, and you get sort of blurry reconstruction of the image, but now you can definitely see what was going on there, okay? So it means that the information is still here. it has not been lost. So the computer vision algorithms still have a reasonable hope of recognizing the object, which makes sense because otherwise people wouldn't have not been using this feature for the past 15 years, right? Now here's what we did compared to what they did with hog features. So this is their reconstruction, and this is what we get if we, instead of doing their trick, which is actually fairly complicated, we simply optimize the loss function. As you can see, we can get even better reconstructions, which are much more detailed. We can even reconstruct the details of the eye here, which is very, very surprising. That just means this all just means that this representation actually contains a lot of information about the image, a lot more than was thought. And it's also a nice validation of our inversion method. It works pretty well. Okay. Now you can take variant of hog. So this is hog in the, as you're familiar with it, in the implementation of Gershik et al., which is what is used in the form of parts model. If you don't know what it is, doesn't matter. Okay. Now you can tweak it slightly and change in such a way when the gradients are accumulated in this histogram used by linear interpolation with respect to the angle of the gradient, which is not something that Ross Gershik and et al. Do, but which was done by Dalal Triggs in their original hog. Now, because now the representation is more continuous, it's actually easier to invert, and you can get even better reconstructions out. Okay? Or you can apply the same to dense shift instead of hog, and the reconstruction is better still, probably because dense shift is even more redundant than hog. And here we choose parameters for dense shift to make it as similar as possible to hog, by the way. If you don't understand what it is, doesn't matter. But for the ones that appreciate this, can actually be an interesting bit of information. Okay, so hog is fine, solved in a way, or at least solved what concerns visualizations. This is what happens when you do it on CNNs. I'm going to show many examples of that, but this is the basic story. So the first couple of layers are essentially invertible. Okay? So COM1 in particular gives you a reconstruction which is nearly identical to the input image. So here's an image of a monkey being reconstructed. As you go deeper down in the architecture, the reconstruction is still quite photorealistic. You remember roughly the colors, definitely the shape. It becomes blurrier, but you can still definitely recognize the input image. Now, this is the last convolutional feature level is here, max pooling in number 5. You can see here that now these parts of the object start to move around when you do the reconstruction. This is an example of the invariance of the architecture to this type of deformation in the image. What this means is that if you feed the architecture this image here, or that image there, and you compute M-pool 5 features, then they would be indistinguishable from the viewpoint of the CNN. So for the CNN at level 5, this and that are the same. Okay? If you go deeper down, then your reconstruction becomes messier. But even at FC, or ReLU 7 in this case, you can still recognize bits of the monkey face. So here I think you can see 2 eyes, but now they've been sort of swapped. You can see the fur and so on and so forth. Now it's a bit like reading tea leaves, I admit that. But if you look carefully, you can definitely see these patterns. So you have an idea that at this level, the network has been decomposing the image into different bits and mixing and matching them, right? Here's a zoomed-in version of the same for a different image for the very last convolutional features. Fully connected features. Now, this is particularly interesting because the final features are 1,000-dimensional codes, which ideally is a bit which tells you which class your object is. But actually, it's not, because if you invert it, I think it's pretty clear that you can still capture some elements which are characteristic of this particular image. So even at that deep level of abstraction, you're still remembering quite a lot of information about your input image. Okay, this is very non-trivial. Yeah.
How much does this reconstruction depend on the regularization term?
So if you, I wish.
Is it possible that we just use the wrong regularizer and thus we can?
No, I mean, so the regularizer is actually pretty dumb. All it does is guaranteeing that the image is not too. So it's removing high-frequency component from the image. That's all it does. So it doesn't have any notion of objects or shapes or anything like that. It just the reason why this is important is because this is a discriminatively trained model. The model is not trained to do reconstruction. So the first thing that it does, it removes all the information which is useful for recognition. And this is all the information which is always appearing in all natural images. And the first thing you know in a natural image is that you're going to have a smoothness. So the first thing that the network does is sort of forgets about the smoothness in the image, which makes perfect sense, because that's not that useful for recognition anyway, because you're guaranteed to have smoothness as a for very general statistical natural images anyways, so it would not be discriminative information, okay? So now we're putting this back by using this trick. But again, it's a very light touch. The realization is very, very light. Just allows you to interpolate between values and get a more interpolable reconstruction in that sense, but this is all it does. Here's more examples. This is instead from MPool 5, but what I wanted really to show, well, works very well for many different objects. You get actually pretty pictures, I guess. It's actually a fun topic to work on. Now, videos, right? So you can do the inversion on videos as well. And now what is interesting here is that we're doing the inversion for individual frames. So we're not trying to keep the continuity of the motion preserved. What we're trying to do is to show that the more flicker there is here, the more it means that your network is actually forgetting about geometric details of the image, right? So if this is flickering a lot, it means that all this sort of wobbly version of the image would actually be nearly equivalent from the viewpoint of the representation. So here you can have a pretty good idea of the sort of invariance that there is, okay? Now this is up to norm 2. Now if you go deeper, it starts to become really a mess at some point, but even at COM 5, you can still definitely see that there are definitely some of the features in the input video that are being preserved. Like they're writing here, the lady there, the windshield, window there. You can definitely still recognize some of these objects. And amazingly enough, so this is the last convolutional layer. When you start looking for the fully grounded layers where spatial information is essentially removed, well, it's not actually true. You can still see the guy, right? I mean, it's wobbly a lot, it's really messy, but the part of that information is still there. And if you go deeper, well, now it becomes quite hard to interpret, but you can definitely see that there is a person here which is jumping all around. So, and I think, if you were to slow this down and look at the individual frames, it would be clearer, I guess. But you can get a sense of what information means preserved. Now, the other thing which is interesting is that from the viewpoint of the representation at this level, this image here is exactly equivalent to the input image that you feed it originally. So if you feed that or the true video, you get the same classification out, which is also a way of showing that this network is actually not perfect, because you probably would not classify this necessarily as a human. As a human would classify it as garbage, although you can still barely see humans in there. Okay. So quite a few messages to take home. So this is a comparison between COM1, COM5, the middle of the network, and the last layer. Okay. Now we are working on this further to try to get instead of continuous reconstruction, so to avoid killing people by causing epileptic crisis in the audience. So we're going to see what we can get there. Oh, here you can see, so when the construction works were appearing, you would see actually the helmets flashing around this image, which is quite interesting. So again, parts being captured. Okay? Okay, so this is you can do many other things with this technique. Another thing you can do is study information locality. So as I said, these convolutional features are local, but how local? So here's how you can do it. You can try to reconstruct your image by just using, say, 5x5 patches of neurons. And if you do that from different levels in your architecture, you get these reconstructions. Now this means that as you go deeper in the architecture and you still look at 5x5 neurons, well, these neurons, there's like filters outputs, they have a support which is larger and larger. Now, the white box here denotes the theoretical support of these filters, something you can compute analytically, but the reconstruction is usually defined in the center, much blurrier in the middle, which means that the actual support of the filter is, in fact, smaller than what the math would actually suggest. Okay? And even here, where the math would say that the support of the image, the whole support of the filter is the whole image, actually, in the reconstruction based on 5x5 neurons is pretty centered. And here's another very interesting thing. So if you're familiar with this AlexNext architecture, the guy decided that because it wouldn't fit on one GPU, he had to split the two streams here into two sets of filters, which worked essentially independently up to COM3, I believe, right? But this was done purely for computational reasons. So you split this in two streams of filters, and you parallelize them to the two GPUs for calculations. Now, what it turns out is that if you train this architecture on natural images, automatically, I should say, part of these filters learn color, and part of those filters learn black and white. Not only that, but the color ones are a bit blurrier, in fact, definitely blurrier than the ones that instead focus on luminance. It's automatically learning to separate colors from shape information in a way. Okay, this is remarkable because there's nothing in this architecture that suggests that this should happen. Just the fact that you have two semi-independent set of filters means that filters naturally separate in this way. It's pretty interesting. This was known by looking at the filters. Now we can show that by looking at the constructions. Okay. Deep dreams. What else can we do? So this is actually a follow-up work to an extent to something we did earlier, in which we wanted to only explore what the network will learn about its final decision. So what does the network learn about, say, bicycles? So what we do there is, instead of trying to reconstruct the feature, we simply maximize the feature here, which corresponds to the notion of bicycles, by tweaking the input, starting from random noise and seeing what we get out. So it's very similar, but again, the objective function is slightly different, and now we want just to maximize the class of the image that we are reconstructing. What's this? A girl? No, what's that? Sorry? Flamingos, yeah, okay, it's a kind of bird, yes, it's a goose actually. So the network is emphasizing too much certain colors, but so this has been obtained by taking a single bit and then finding the image which most activates that bit at the end of the architecture, right? Starting from noise. So this is the stuff that Next really knows about GIS, and you can see that it's reconstructing several of them together. So it knows about parts, it knows how to mix and match them, and it knows how to shift them. Okay. Here's another example, abstract art. This is bell peppers. Okay, so I'm sorry to cut you short, but I have to present some more. So, okay. There are many other things you can do for visualization. Well, maybe not many, maybe just a few. So another very good one is the convolution. If you're interested, look into the paper. It was actually Best Paper Award at ECCV 2014. It's kind of similar to what we do, except that they focus on single neurons, and crucially, when they do the inversion, they feed some information from all intermediate layers, not just the last one, which essentially destroys your ability of checking which information is actually being preserved here, because you're actually using information from the previous layers as well. So this answers a different question from the one that I just showed you. Okay. All right, so now let me move to the last part, and I kept for the last part the hardest one, obviously. So bear with me for another 10 minutes. I think it's worth knowing where we're going here. Okay? All right, so this visualization. Next is trying to understand even more about this architecture. And so what we're looking here is equivariance and equivalence of representations. So what should the representation do? Well, the intuition that computer vision people had, and maybe also some machine learning people had, but maybe not all of them, for quite a long time, is that what we want to do is that we have a semantic similarity, so two images which have the same category, and we want our representation to map that into a corresponding vector similarity or distance between Euclidean vectors. So this is exactly what this means. So you have three images, and two contain bicycles, so they are congruous, and two contains a bicycle and a dog, so they're incongruous. Then you want these two vectors computed by the representation to be close, and these two to be far apart. Why? Because if you have that, and your scoring function, which is the basis of your classification, is smooth, so slowly varying in this Euclidean space, then it means that this function will assign similar labels, similar scores to these 2 points, and potentially scores which are different for these 2 points. So you're essentially matching your notion of continuity into this space to your classification problem. So it makes sense. But does it? Well, this corresponds to this idea that the feature, a good feature, is invariant to nuisance factors. It means that if you change viewpoint or you change the model of the bicycle, you don't really want your vector to change, but sensitive or distinctive for semantic variations, for stuff that you want to tell apart. Now, distinctiveness and invariance have been sort of the, well, two pillars of researching image features for a long time. However, it's probably not per se by itself a very good idea. Why? Well, because invariance is in fact entirely task dependent. So if you have 2 cars and you want to tell these are 2 cars, well, these 2 vectors should be near. But if you want to tell whether these objects have the same color, well, these 2 should be far apart. So there is no single representation that is invariant for all tasks you want, because that would be the true representation, which is just the constants, right? So you cannot be invariant to both these things at the same time distinctive for both. So what do you do instead? Well, you ask your features to do something else. And there are several things you can look for. One is equivariance and invariance. What is it? So here we have an image. And now we take that and we transform it. So we say we do a vertical flip, horizontal flip like that. What we can ask is, what happens if now we map this guy into the representation space by computing phi of g of x? In particular, what we want to answer is, what is the mapping which goes from here to there directly? Can we characterize that? Or we could do a rotation and then ask ourselves, what is the mapping that goes from that to there? And of course, this should be this should work for any image that we could provide as input. So this is what we call equivariance. It means that we change the input in a certain way, and there is an equivariant transformation which affects the output. This is how it works formally. So we have an input image x. We compute features which are convolutional in nature. So they're represented here by a grid of values. Or we compute this guy. We take this guy. We compute the transformation of it. We rotate it. We compute the features. Now, this means that this information is shifted around because these features are local, and now the local information has been moved around a bit. But also the color, which encodes the value, is different because, for example, a filter which is vertical before now would correspond to a filter which is horizontal. So things are sort of changing, and the values of these vectors would also be incompatible. Now, we'll ask ourselves whether there's a mapping which goes from here to there, which can sort of close this diagram, make it commutative. Now, there are three cases. Either this map here depends on both x and g, in which case you don't do anything because you're essentially computing g of x and then compose that with phi. So if evaluating M requires you to know about x and g, you're not doing anything. Or this map depends only on g, in which case, and not on x, in which case you have equivariance here. Okay? It means you can predict how this works regardless of the image. Or, in fact, this doesn't change at all. It doesn't depend neither on x nor on g, which means it's constant, in which case you actually get invariance. Okay, so equivariance, invariance, or nothing at all. Here's how this works in a practical case, hog. So we have an image, we compute hog features. We have the same image rotated, we compute hog features. And now, instead of going this way, we want to go that way and then finding mapping mg that rotates the features directly. Can we do that? Well, it turns out that yes, we can for many representations. It's very hard to see from hog, but now we can invert it and check whether the results make sense, and it does. So now, if you reconstruct your image from these features or the ones which have been obtained by transforming the features themselves, not the image, well, you get something which is very, very similar. So it has worked. Okay? Now, the goal of doing this is to study how transformations affect the representation. Okay? Keep that in mind. We can do that for other effects, for example, downscaling, which case also works, and you can do any other rotation, flipping, and so on and so forth. Now, how do we find this MG in practice? Well, for a hog, we might actually think to do that analytically because hog is an analytical feature defined formally through math. But for CNNs, we cannot do that because that's being learned. So we're going to need to learn that too. So how do we do it? Well, the other thing we want is this MG to be as simple as possible. For example, a linear transformation. Why do we want that? Well, first of all, because if phi was invertible, which isn't, but if we were, then what we could do is take phi of x, invert it, then apply g, and get back there. So that would be trivial. So that's not very interesting. But remember that phi, in fact, is not invertible in general. But most importantly, if MG is simple, like a linear filter, then it means that the next level on your representation, which is composed linear filters, can actually do something about transformation of the input image. Okay? So if you can prove that this transformation is simple and linear, then that corresponds to your network ability of further processing this in a way which would reflect this transformation potentially. Okay? So we pose that as a regularized regression problem, ridge regression. But in fact, we can do better because these are convolutional features. So what we can expect is that if we want to predict the feature values here, well, then we can try to backtrack where the information should come from this pixel because of the convolutional structure, from that pixel because of the rotation, then from that pixel, from that features because of the convolutional structure again. So to get this value here, probably we should try to predict evaluate M on these 4 values there. So we keep the computation local, which we can do quite effectively and simply by having this permutation layer. So we take the input image, could be the feature, swap around these elements in such a way that we align them with what we think they should align to here up to the transformation, And then we have a convolutional layer, which actually sort of changes the color of these features in the sense that it changes the value, makes them compatible. Because permutation is not enough. You also have to operate across feature channels to link them back. Okay? So we decompose our MG as a permutation layer, followed by a convolutional layer. And we learn permutation layer is done analytically by knowledge of the transformation G you're trying to approximate, and AG is instead learned. So we can do two things to evaluate this. One is what we did before, check whether following this path or that path gives us the same features or not. Or, well, we can check whether we can, in fact, undo the effect of a transformation and still have features which perform well. So what does it mean? It means that if we have a rotated image, we can compute the features instead of rotating the image back. Now we rotate the features back, so these two should be equivalent. And now if we perform classification of the image, either from that or from that, if we did a good job with MG to the -1, then it means that the classification performance will be the same. It means that by transforming the features, we can classify either the original images or the rotated images just equally. Okay? And this is what we do to go beyond HOG and work with CNNs. Because that's a much more interesting thing to check for. Instead of just checking qualitative performance, we check quantitative performance. And so here's how this works in practice. So here I have a baseline CNN, then we flip, for example, the image, and now we want this CNN to work just as well, but in fact, just flipping the image like that would break it. So we're going to try to fix this by inserting a layer in between that tries to undo the effect of transformation, and then we try to apply this layer at different depths, always working with convolutional features, although, in fact, you could also do that for fully connected layers, but we want to use our approximation, which is local and sparse. Okay? Now, this is a sort of how this performs on measured in terms of classification on the ImageNet validation dataset. So this would be flipping horizontally the image. This is the baseline performance. So this is a standard AlexNet classifier, which gives you 41-ish% top 5 classification accuracy. Now what we're going to do is to flip the image. So if you do that, well, in this case, actually nothing changes. So take the image, flip it, classify it, still fine. Can you guess why? Because data augmentation, because the network has been trained to recognize already flipped version of the image, so it's invariant to that. So many objects are symmetric to horizontal flips, horizontal flips in natural images. So the network, by training it in natural images, or maybe because of data augmentation, is invariant to that. So no, we flip doesn't matter. So in this case, our method doesn't do anything at all. It keeps the performance constant if you insert this transformation layer in the middle. So this is just a sanity check. But now, this is what happens if you do vertical flips. Now it breaks. So your 40% or so top 5 classification accuracy goes to 75 or so. So quite a lot worse. But if you insert this compensation layer in the middle, then this goes back quite a lot. Not exactly to the original performance, but quite close. And importantly, as you would expect, it works better if you try to undo the transformation earlier in the architecture, where you have these early convolutional features, and a little worse if you do that later. Now, why is that? Well, our conjecture is that this happens because the first features are actually fairly generic, and they're just doing some sort of low-level intermediate processing. So those are the ones that are actually easier to invert for any transformation. Whereas the more you get down to the architecture, the more specialized these features are, you might end up doing something, you might end up computing things which are actually not as easy to undo geometrically. Okay. Downscaling works as well. And applications. Okay, so this is just fun application, but it's actually at the same time a serious one. Suppose you want to detect the cat face pose. This is why it's fun. It's just a silly example. Now, the typical way we would have been doing that in Vision would have been to take X, undoing the affine transformation which affects the cat face, and then associating to that a score by computing a feature out of that, warped image, and then a linear classifier. Now, what you can do is the same, but instead of warping the image, you warp the feature fields directly. Okay? Now, this is a lot faster, typically, because you do not need to recompute the transformation for all the transformation you want to try. And this works also for any object, of course, you put in there. And if you try to compare this and that quantitatively, you're going to see that it works just as well, but faster. Okay? So this is actually quite useful for, potentially quite useful for essentially structure auto prediction of pose. And I'd like to spend just 2 minutes just telling you about equivalence, and then I'm going to stop, I promise. This last concept, I think, is also a very interesting one. When you work with deep learning, you end up having different representation if you learn on the same data set twice because of different seeds, or if you train from 2 different data sets altogether. But the question is, we train representation which have very different numbers in them, but are they actually extracting different information from images or not? So are these 2 representations equivalent? Can we map this feature to that to resolve this difference? And this is the notion, it's actually a fun one, Franken networks. So we want to test whether this is actually possible. So what we do is we take this network, CNN AB, and this network, CNN normal, just 2 networks. And we ask ourselves whether these first 5 convolutional layers are actually equivalent to these ones. So how do we test it? Well, we simply sever this network here and there. So we chop the sort of legs of that and the head of that, and we stitch them together by inserting a learning and stitching layer in between. Okay? And this is simply a convolutional feature layer in between. Okay, so you get this CNN AB normal, and you try to see whether this performs as well as your original architecture CNN normal on this original task. Okay, so you want basically to see whether you can replace these convolutional features with those and see whether they perform just as well. If you can do that, if you can learn this compatibility layer, then it means that this feature, effectively, we're computing whatever those features were anyway. So they're not really different. They're just different in appearance, but not really substantially. So we did that, training either an ImageNet with 2 networks, AlexNet and VGGF. So these have similar goals, but completely different parameterization because they've been trained from scratch, and so the numbers are completely compatible. And then we did that by training a 3rd network on, in fact, this was trained by MIT, on their dataset CNN places. So here's what happens when you do this stitching at different depth in your architecture. So baseline performance, 40% or so for AlexNet. If you take, I guess, AlexNet and you replace the first convolutional layers with the VGGF and you don't do anything, then the performance is destroyed. So this goes from 40% error to 100% error. Doesn't work, which is what you would expect. If you train a layer, this compatibility layer, actually you recover most of your performance. It means that you train 2 different models, but actually you train the same stuff to a large extent. So these networks are actually equivalent, although they don't seem to be equivalent if you look at the numbers. It's quite interesting, I thought. And you can do the same for this data set places. And now something similar, but not quite the same happens. So the equivalence works quite well for the first convolutional layers, but then it degrades for the later ones. I mean, it's still much better than not doing anything. So you can still perform to an extent reasonably, but definitely the gap is much larger. Why? Well, again, the conjecture, which is an obvious one, is that the deeper you go into the architecture, the more specialized your features are. Now, this type of experiments might suggest, for example, which features are genetic and which aren't, and how you should merge or extend them or complement them to train on different tasks, for example. Okay. So it has actually quite a practical use in practice, but it's also a theoretical insight. Okay, so that's all. Just to summarize, what I show you today is CNNs are a good tool, especially if you want to be lazy. You just throw lots of data to big models and perform very well. Now, what we would like to do moving forward is get better architecture, but at the same time get a much better understanding of these architectures. And we're trying to do this in 2 ways. One is through visualizations, and the other one is by studying properties of networks. For example, functional properties like equivariance and equivalence. There are many other things we're going to be able to do moving forward in this area, because I think this is just scratching the surface of what is actually possible. All right, so thank you very much, and if there are questions, I should be able to take them.
Okay, we have time for a limited number of questions.
Yep.
Thank you very much. It was very instructive for all of us, I think. And I would like to ask about the size of the mini batches. Somewhere in your talk, you said that the mini batch size should contain about 1/5 of all of the number of classes.
That's right.
Are there any theoretical bounds or papers about it? It's just
no. That's a completely empirical result, unfortunately, and it's a bit even hard to justify in my mind. I guess really, so you should have at least some level of averaging happening in these mini batches, and I guess probably if you try to train with too many, I mean, in order to start training the earlier layer, you need to be able to see over and over again the same concept. Now, if your data set is number of classes is too large, before you visit again the same class, it will pass too much time, such that you can actually do anything useful with that information. No, there are no theoretical bounds I know about, but and even 1/5 is completely empirical, right? So maybe for different application it will be 1/4. Oh, 1/42, who knows? Yep.
Dr. Vedaldi, can you share some experience about using convolutional restricted Boltzmann machines for pre-training of deep conv nets?
Okay, the short answer is I can't, because I never used Boltzmann machine myself, unfortunately. So I've been a Fisher vector guy for a long time, well, not Fisher vector, but kernel learning guy for a long time. And we started working on deep nets when AlexNet became popular 2 years ago. So we mostly focused on discriminative machine deep learning. We didn't really work much with Boltzmann machines. Having said that, they're probably quite useful, but I cannot really comment more than that at this time. Yep.
More questions?
Quite.
Maybe one tip on training deep networks. Maxim Milakov on one of his talks said that you should always change one parameter when you tune your parameters. Just maybe add one layer or change a batch size or learning rate or something like this.
Yes.
As we see with these giant networks, it's really expensive to compute it. Every experiment is really expensive.
Yes.
And maybe you could share some tips. Maybe when you add layer, you should make a learning layer, a learning rate smaller or something like this, or you do just that's pure experience and one change at a time.
Our mantra is also change one parameter at a time. That's sort of a holy grail rule, right? Yeah. It's very important. But okay, in practice, I think there are two ways around that. One is Bayesian optimization. I have some very good people in Oxford that do that. Although I didn't really experiment yet with it, that would be probably the way to automatize it. Okay, are you familiar with it?
Thank you.
No, I'm asking, are you familiar with it?
Yeah,
okay.
I read
okay,
few
so Bayesian
papers, but I didn't
so now the other
try
thing,
it myself.
Okay, fine. So me neither, actually, but I know that it's quite a reasonable thing to try. The other thing is that, so one of the hopes that we have for these visualization experiments on equivariance, invariance, and so on, is to suggest which layer of an architecture does what. So when you do transfer learning, for example, and it doesn't work as well, probably it doesn't make sense to try to optimize the first 3 convolutional layers. Probably you should try to do something about the 4th one, say. So by having insights of what each layer does, you might have insight of how well each one is likely to transfer between problems, and each one should be instead changed or increased or improved to address a new one. Now, all this is a very hand wave at the moment, but our hope is that as we're going to get better insights on what the architecture actually do, we're also going to be able to direct our efforts in optimizing them much better.
Yeah, thank you. Once I had an idea of dynamic change of learning rate depending on our errors, do they change or something like this? Okay.
It makes sense, but sure. Okay.
Yeah, thank you. Thank you very much.
Okay, should we say the last question? Oh, okay, maybe not last. Last two.
Make them easy, please.
Thank you for the talk. I wanted to ask whether this technology could be expanded to recognize 3D data from Kinect or something, or it would be computationally infeasible.
Sorry, to do what?
Kinect data.
Kinect
Kinect
data.
data.
3D data, 3D points, sets.
I don't see why it would be hard. No, I think from one single image or for a video stream for 3D reconstruction. So Kinect data can be just like a depth map.
To recognize from not usual images, but with 3D data. No, I mean for the same tasks.
Oh, you mean recognizing an object in 3D?
Yes.
Yeah, I'm sure it's feasible now. Okay, so that would be a volume, basically. You want to work with a volume. This is what you mean.
Yes.
Okay. Well, look, okay, so the cheap answer is you can project the volume on a depth map, and then that's an image. And people do that. Okay. The slightly more elaborate answer is that these volumes are 90%, 99% empty, so you only care about the surfaces, really. So you need to exploit that, I think.
If you add to data not only flat image but also depth.
If you have both, then it's quite easy to integrate multiple inputs in the network, and you can have a part of the network which processes one bit, another part which processes the other bit, and then you fuse these feature streams down later in the architecture. It doesn't need to be a sequence, of course. It can be a DAG, like a direct acyclic graph. So in that sense, you could have a part of the network that does depth and a part which does RGB and just merges the two quite easily, I think.
Yes.
Yep.
Thank you.
Okay, and the last question. Okay.
Hello, and thank you very much for such a good lecture. I will ask one question. Will your network learn itself?
Learning themselves.
Themselves, yes.
Interesting question, right?
Or will or can?
Can learn themselves. Like you mean without training data? Without labels. Okay, unsupervised learning. Interesting. I would definitely hope so. There are many people working on it. You can have you can find tricks like getting weakly supervised labels, noise labels, by using, well, I suppose Yandex image search or Google image search, which is what we did in the past. Now, there are things that might actually work well for as auxiliary tasks to train networks. One of them could be, are you familiar with the word to vec? It's this encoding that Google came up with for textual words, actually. So the way they do that is they train a network to predict a word given its context or vice versa. Now, that's entirely unsupervised. You just need lots of textual data to do it. And you can apply that to images as well. So I think that would be a promising way of trying to do that. Then, of course, there is the whole autoencoder business, Boltzmann machines and all those generality models, which, again, I cannot venture in commenting about yet. So I'm sure that's also very promising. Yeah, plenty of ideas. Will they be able to achieve that? I think at the end of the day, what we'll be able to discover is that by learning from multiple tasks, some of which are unsupervised, and just a little bit of supervision, we'll be able to do very well.
Okay, and the very last question, and then we'll take it offline.
Right.
So my question is a little bit unrelated. So what's your opinion on whether we can learn in terms of problems concerning time series using deep networks and auto-generation of features for those problems like anomaly detection?
Anomaly detection, I'm not sure. I should think about it. I guess anomaly detection is difficult for a discriminative model, isn't it? Because you're not really trying to capture a statistical regularity in the data. Just if you don't have examples of faults, then telling them apart from good data with a discriminative model might actually be quite hard. You would need probably a generative one, I would guess. But in terms of sequences, many people are now using recurrent networks and LSTMs and those things, which seems to be naturally tailored to process sequences of data. Some people have been doing that for videos, or will be doing that for videos in the upcoming conferences anyways, which has also a sort of sequential nature due to time. In the case of images, it's less obvious how you would actually find sequences in them, right? So an image doesn't have a natural linear structure per se, or sequential structure. Now, if you're asking me whether these LSTM are any good or not, again, because we didn't really try them directly yet, or we're just starting to try them, I wouldn't know what to answer. In terms of direct experience, what I can tell you is that many people are now using them, and they seem to be pretty good tools. So it's definitely worth investigating them.
Okay, so let's thank Andrea for the fantastic talk.